Hi, I'm Sümeyye Baba, and I'm studying Electrical and Electronics Engineering in Bilkent University. I will perform my Physics 101 project experiment, which is conservation of angular momentum and also observing the moment of inertia. Angular momentum is the property of a rotating body given by the product of moment of inertia and angular velocity. If the net external torque is zero, then the angular momentum can be conserved. Moment of inertia is the quantity that determines the torque needed for desired angular acceleration about the rotational axis. It depends on the mass distribution of a body and the axis chosen. Angular velocity is how fast the angular position or orientation of an object changes with time. So let's get to my experiment.
So we have two same magnets and a disk. I will give a brief force to start rotation for the disk, and right after I press the pedals, as you see, the angular velocity from that screen of rotational dynamics apparatus will be recorded. Then I will start to put the masses as close as possible to the center of the platform, one by one. After every revolution, the angular velocities again will be recorded. Let's do it. I will put the masses as close as possible to the center of the disk, as you see. And also same for the other. The process will be like this. After recording angular velocities, with a ruler, I will measure the radiuses of the magnets and the disk. And also, with a scalar, I will measure the masses. The masses and the radiuses will be used to calculate the moment of inertias, and then the datas will be compared.
This is the mass of the disk, the mass of the magnet, the radius of the magnet, the outer radius of the disk, and the inner radius of the disk. These data will be used to calculate the moment of inertias. For the disk, we will use the formula for the hollow cylinders, and for magnets, we will use parallel axis theorem because the magnet rotates about an axis which is parallel to its center of mass. And we will use the angular velocity data to observe the conservation of angular momentum. For example, these are the data when there is no magnet on the disk. You can see the angular momentum result. And these are the data when there is one magnet put on the disk. The angular momentums you can see close, but not the same due to the errors. But we can see that the angular momentum is nearly conserved if we, neglect the errors.
For second part, we have the same magnet and the same disk, and I will again give a brief force to start rotation, and right after pressing the pedals, the angular velocity will be recorded. Then I will put the magnet on the disk and again record the angular velocity from the screen. I'll repeat it for each step with changing the position of the magnet like this. I measured the radiuses and the masses of the disk and the magnet, so we know them. These data will be used to calculate the moment of inertias again. Let's show the process. So for one step, I put the magnet on the edge of the disk. For example, for another step, I will put the magnet here, closer to the center of the disk, as you can see. That's my process.
For each step, I compared the initial angular momentum and the final angular momentum. The initials were when there was no magnet on the disk, and the finals were when there is one magnet put on the disk. If we see this fraction, we expect this fraction to be 1 because the angular momentum will be conserved because there was no net external torque on the system. But these are my datas, and you can see it's not 1 but close to 1. So we can say again the angular momentum is conserved. Due to the energy loss because of the friction, the angular velocity datas have been affected, and this also has affected my results. I also did my measurements with a ruler, and I didn't get the perfect exact measurements. Because of this, the perfect exact results didn't occur. I had some errors, so these were the reasons of errors.